Before we dive into today's journey through plate tectonics, a quick favour. If you enjoy this kind of science content, please remember to like the video, subscribe to the channel, and share it with someone who loves learning about our planet. It really helps the channel grow, and I appreciate your support so much. I am also curious, what time is it where you're watching right now, and where in the world are you tuning in from? Let me know in the comments below, and now let's begin. Earth turns slowly beneath a cover of oceans and continents that seem solid and permanent, a familiar surface of water, basins, mountain chains, plains and coastlines that defines the world of living things. The blue areas of the planet, the linked global ocean, fill deep basins that stretch for thousands of kilometers, while the continents rise as irregular blocks of lighter rock that stand higher than the surrounding seafloor. From orbit, the pattern looks fixed like colored areas on a globe. Yet this shape is only one arrangement in a long sequence of changing maps, because the solid surface that carries oceans and land is only a thin outer shell, resting on layers that move slowly over geological time. The outer shell is called the crust, and it forms the visible face of the planet, but in terms of total thickness it makes up only a very small fraction of Earth. Beneath it, hidden from direct view, lies a much thicker layer of hot, slowly deforming rock called the mantle, and below that a dense metallic core. The familiar shapes of continents and ocean basins exist only on this uppermost crustal skin. The crust differs in thickness and composition from place to place. Under the continents, it thickens into a lighter, more buoyant layer made mainly of rocks rich in silica and aluminium. Under the oceans, it is thinner and denser, mainly basalt, a dark volcanic rock that forms when magma rises and cools along the mid-ocean ridges. These differences mean that continents ride higher like rafts of lighter material, while the ocean basins sit lower, filled with water. The contrast between the heights of continents and the depths of oceans gives the planet its present topography, but the overall crust remains thin compared to the radius of Earth, more like a delicate shell than a solid body. If the planet were reduced to the size of a common piece of fruit, the crust would be no thicker than its outer skin, easily cracked, difficult to notice from a distance. This thinness is more than a simple physical detail. It means that the accessible surface is closely coupled to the deeper interior, so that slow processes inside the planet eventually express themselves as changes on the surface. The oceans that seem permanent are held in place by the shapes of the basins they occupy, and those basins exist because of how the crust has formed, shifted and been recycled over hundreds of millions of years. Mountains that appear immovable are only the latest growths along great belts of deformation, built as crust is compressed, thickened and uplifted. Low coastal plains and broad continental interiors reflect long periods of relative stability, but even these regions bear the traces of ancient collisions and separations in their rocks. To understand how plate tectonics creates continents and oceans, it is necessary to see the crust not as a static outer layer, but as part of a larger system powered from below. Heat from the interior rises through the mantle, and over long spans of time this heat causes parts of the mantle to flow slowly, almost like an extremely viscous fluid. Above this moving mantle, the rigid crust does not bend smoothly everywhere. Instead, it is broken into numerous separate pieces, each one rigid on human timescales, but mobile on geological ones. These pieces are the tectonic plates, and they carry the continents and ocean basins as they drift, collide, and pull apart. The present distribution of land and sea is the combined result of countless such interactions. The patterns of mountain belts, the positions of deep ocean trenches and the winding mid-ocean ridges all mark the boundaries where plates meet. In some places, plates move apart and new ocean crust forms. In other places, one plate sinks back into the mantle under another, Elsewhere, plates slide past each other horizontally. Each type of boundary has a characteristic set of features and hazards, and together they define the dynamic framework within which continents and oceans evolve. From the perspective of everyday experience, these motions are too slow to perceive directly. Plate motions occur at speeds comparable to the growth of fingernails, progressing only a few centimeters each year. Over a single lifetime, a continent changes position by only a small distance. On the timescale of hundreds of millions of years, however, those small yearly movements add up to whole oceans opening and closing, and supercontinents coming together and breaking apart. Rocks preserve a record of this activity. On continental margins that now face open ocean, there are often ancient mountain belts and deformed sediments that tell of earlier collisions. Far inland marine fossils appear in regions that stand high above sea level, today showing that parts of the present continents were once beneath shallow seas. On the ocean floor, magnetic patterns in the basalt crust trace the gradual widening of basins as new material forms along spreading ridges and moves outward. Together, these lines of evidence show that the crust behaves like an active shell constantly reshaped. The thinness of the crust also raises questions that extend beyond simple description. Why does Earth among the rocky planets of the inner solar system maintain such a mobile outer shell, while bodies like Mars and the Moon appear more rigid and inactive? What combination of internal heat composition and the presence of water allows this thin crust to fracture into moving plates rather than locking into immobility? The answers are still under study. Many models suggest that the balance between crustal strength and mantle convection, modified by the presence of water in minerals and at plate boundaries, plays a critical role. What is clear is that this balance has made Earth a planet where the surface is continually renewed. Continents have not always occupied their present positions, and oceans have not always filled their current basins. The history of the planet is not a story of a fixed map, but of a restless surface, where plates reshape the crust, and in doing so continually redraw the boundary between land and sea. In this framework, the continents and oceans seen today are a single chapter in an ongoing narrative driven by processes that originate far beneath the familiar surface. Beneath the thin crust, the interior of Earth forms a series of layers that differ in composition, temperature, and behavior, and together these layers act as the engine that drives plate tectonics. The outermost layer of this engine, immediately under the crust, is the uppermost part of the mantle. The mantle is made mostly of solid rock rich in magnesium and iron, but the high temperatures and pressures inside Earth mean that this rock can slowly deform and flow over long periods of time. The mantle is not a pool of liquid magma in the everyday sense. Instead, it is mostly solid, yet it behaves plastically on geological timescales, allowing slow motion that would be impossible in brittle rock near the surface. The crust and the very top of the mantle are mechanically linked, and together form the lithosphere, a rigid layer that breaks into tectonic plates. Beneath the lithosphere in the upper mantle lies a more weakly deforming zone where rocks are closer to their melting point, and small amounts of partial melt may exist between solid grains. This region allows the rigid plates above to move sliding over a mantle that is solid but not perfectly rigid. Seismic waves from earthquakes recorded by networks across the globe provide much of the detailed information about these layers. As the waves pass through Earth, their speeds and paths change depending on the properties of the materials they cross. Careful measurements show that wave speeds increase and decrease at certain depths, marking boundaries such as the transition between the upper and lower mantle. These changes indicate variations in mineral structure where the same basic elements arrange themselves differently under pressure. Experiments in high-pressure laboratories using presses and laser heating recreate some of these conditions and test how minerals transform at depth. Together, seismology and laboratory studies reveal a mantle that is layered but still connected with material able to move from one level to another over long timescales. Deeper still lies the core, divided into a liquid outer part and a solid inner part. Seismic waves that cannot travel through liquids disappear beyond a certain distance from earthquake sources, showing that the outer core is molten. Waves that can pass through solids but not liquids take special paths that outline the size of the inner core, a dense central sphere of solid metal. The outer core is thought to be made mainly of iron with some nickel and lighter elements, and its temperature reaches values comparable to the surface of the Sun. The inner core, despite its high temperature, remains solid because the pressure at Earth's center is extremely high. Under these conditions, iron is compressed into dense crystalline forms, and the melting point is raised above the actual temperature there. This combination of hot, slowly convecting mantle rock above and a liquid metallic core below creates a complex internal heat system. Heat comes from several sources. Some is left over from the formation of Earth, when countless impacts and gravitational collapse heated the young planet. Some arises from the decay of radioactive elements in the mantle and crust, which release energy steadily over billions of years. Some is generated as the inner core continues to grow, with latent heat released as liquid iron solidifies at the inner core boundary. This heat is carried outward by conduction, where energy moves through matter, and by convection, where hotter, less dense material rises, and cooler, denser material sinks. In the mantle, convection takes the form of very slow, large-scale circulation. Hotter regions deep in the mantle tend to rise, while cooler regions near the base of the plates tend to sink. The exact pattern of this circulation is still under investigation. Some evidence suggests that parts of the mantle overturn in long column-like upwellings and broad downwelling sheets, while other evidence points to more complex time-dependent patterns. Tomographic images constructed from variations in seismic wave speeds show narrow zones that may mark subducted slabs descending into the deep mantle, and broader regions that may represent hotter rising material. The outer core also convects, but in a different way. In the liquid metal of the outer core, motion is much more vigorous than in the mantle, and this motion, combined with Earth's rotation, is thought to generate the planet's magnetic field through a process known as the geodynamo. The magnetic field shields the surface from much of the charged particle radiation in the solar wind and guides compasses, but it also leaves a record in rocks. As basaltic lava cools at the surface, magnetic minerals inside align with the current direction of the field and lock in that orientation. Over time, these records show that the magnetic poles have reversed many times, with north and south exchanging roles. The pattern of magnetic stripes on the ocean floor, arranged symmetrically on either side of mid-ocean ridges, helped confirm the idea of seafloor spreading and plate motion. Yet the deeper behavior of the core remains only partly understood. The exact composition of the outer core, the nature of the solid inner core, and the detailed pattern of flow that sustains the magnetic field are still subjects of active research. There are hints that the inner core may not be uniform, that its crystals may be aligned more in some directions than others, and that its growth may be uneven over time. These features could influence how heat leaves the core and how convection patterns form in both core and mantle. Small changes in the deep interior might therefore have long-term effects on surface processes, including the style and speed of plate movements. One of the central questions is how the heat generated and stored in the interior translates into the specific pattern of plate tectonics observed today. The mantle clearly convects, and the plates clearly move, but the precise way in which mantle flow drags, pushes or resists the plates is still being refined. Some models emphasize the role of sinking slabs at subduction zones, which pull the trailing plate behind them as they descend. Others highlight the push from mid-ocean ridges, where warm, newly formed crust slides away from the elevated ridge axis. The viscosity of the mantle, which measures how resistant it is to flow, may vary by several orders of magnitude between different depths and regions, and this variability shapes the paths of convection currents. Even with modern seismology, satellite gravity measurements and laboratory experiments on rocks under extreme conditions, many details remain uncertain. What is clear is that the layered interior of Earth, from lithosphere through mantle to core, forms a linked system in which heat composition and mechanical strength interact. The crust which carries continents and oceans responds to slow forces that arise far below in places never directly observed. This hidden engine sets the stage for the movement of plates, the opening and closing of ocean basins and the rise of mountain ranges, but its full pattern is still being mapped. The incomplete picture of these internal motions leaves open questions about why plate tectonics takes its present form, how stable that form is, and how it might have been different in the distant past. When Earth first forms from countless smaller bodies in the early solar system, its outer layers are far from the organized pattern of moving plates observed today. The young planet is heated by impacts by the decay of radioactive elements and by the separation of heavy and light materials into core, mantle, and crust. For a time, large parts of the surface may be covered by a deep magma ocean, a layer of molten rock slowly cooling and crystallizing. As heat escapes into space, the outermost layer solidifies into a continuous shell of rock. This early shell is thick in some places and thin in others, marked by giant impact scars and zones of intense volcanism. Over time it cools and strengthens. In principle, such a shell could remain as a single unbroken lid for billions of years, as seems to have happened on some other rocky bodies. Instead, on Earth, it eventually fractures into a complex mosaic of separate blocks that start to move relative to one another, forming the modern system of tectonic plates. The transition from a single outer shell to a mobile segmented lithosphere is one of the key steps in the history of the planet, yet it is still not fully understood. The lithosphere is the combined rigid layer of crust and uppermost mantle. It acts as a mechanical unit bending braking and transmitting forces. Beneath it lies the warmer, more deformable mantle that can flow slowly over geological time. As the planet loses heat, the lithosphere thickens and stress builds within it. Convective motion in the underlying mantle also exerts drag on the base of the lithosphere, pulling in some regions and pushing in others. These processes introduce horizontal forces in the outer shell. Where the shell is weak, perhaps due to inherited impact structures, long-standing zones of hot upwelling mantle, or variations in composition and thickness, it becomes easier for fractures to form and propagate. Over tens to hundreds of millions of years, these fractures may link up into continuous boundaries that outline distinct plates. Observations of the present plates show that they vary greatly in size and shape. There are several large plates that each carry major ocean basins or continents, and many smaller plates sandwiched between them. Together they cover the surface without leaving gaps fitting against one another, like an irregular shifting puzzle. Their boundaries are picked out by belts of earthquakes, chains of volcanoes, and linear geological structures on land and sea floor. Satellite-based measurements of ground motion using techniques such as global positioning systems show that points on the surface separated by thousands of kilometers move relative to each other at rates of a few centimeters per year. When these velocities are mapped globally, they group into coherent blocks, each moving almost rigidly. These are the present tectonic plates directly measured rather than inferred. The fact that the outer shell behaves this way now does not, however, reveal exactly when or how the pattern began. Rocks from the deep past offer some clues. Very old continental regions known as cratons contain rocks whose ages reach back more than 3 billion years. Some of these rocks show signs of processes similar to modern subduction, where one piece of lithosphere sinks beneath another, and of volcanic arcs similar to those above present convergent margins. Other ancient terrains show more ambiguous patterns with thick, stable crust, but less clear evidence of horizontal motions. The record is incomplete because later tectonic events rework, bury, or recycle older structures. As a result, geologists still debate when a fully developed system of plate tectonics with linked spreading ridges, subduction zones, and transform faults first emerged. Estimates range from soon after the planet formed to nearer the middle of its history. This uncertainty is a central part of the mystery of plate birth. Comparisons with other planets sharpen the question. Mars, for example, has large volcanic provinces and deep canyons, but its surface does not show the global network of linear ridges, trenches, and transform faults that would mark active plate boundaries. Its crust appears to have acted more as a single shell with local stretching and compression, but no long-lived planet-wide segmentation into moving plates. Venus has a surface reshaped by volcanism and tectonism, with many deformed regions and mountain belts, yet there is no clear evidence of the systematic spreading and subduction seen on Earth. Instead, the surface may be periodically resurfaced in large episodes. The Moon and Mercury show even older, colder, more static crusts dominated by impact craters and contractional features. Against this background, Earth stands out as the only known world where a thin outer shell is broken into plates that move in a coordinated way over a convecting mantle. A widely discussed factor in this difference is the presence of liquid water at Earth's surface and within its rocks. Water enters minerals and weakens them, lowers the melting point of rocks and lubricates faults and plate boundaries. At subduction zones, cold, wet oceanic lithosphere sinks into the mantle, and water released from the slab promotes melting in the overlying mantle, wedge-feeding volcanic arcs. This continuous cycling of water between surface and interior may help keep the lithosphere weak enough to sustain plate motions. On planets where surface water is scarce or absent, the lithosphere may be stronger and less likely to break into mobile pieces. Another factor is internal heat. Earth retains enough heat to drive vigorous mantle convection, but not so much that the entire mantle behaves as a thin, weak layer under an immobile lid. There seems to be a balance between the strength of the lithosphere and the stress generated by mantle flow. If the lithosphere is too strong, it acts as a stagnant lid and prevents plate tectonics. If it is too weak, it may deform in a more diffuse way without forming coherent plates. Earth appears to lie in a regime where stresses and strengths permit the formation of discrete plates and stable plate boundaries. Yet the exact conditions that set this balance are still being investigated. Numerical models in which the equations of fluid motion and heat transfer are solved on large computers explore how variations in temperature composition, water content, and planetary size affect mantle convection and lithosphere behavior. Some models reproduce plate-like behavior under certain parameter choices, suggesting that Earth's present state is not inevitable, but depends on specific combinations of properties. Laboratory experiments with viscous fluids and deformable lids provide analogues with cool, rigid layers breaking into moving fragments above warmer convecting interiors. These approaches support the idea that plate tectonics emerges naturally when certain thresholds are crossed, but they also show how sensitive the system can be. Small changes in rheology, the way materials deform, can shift a model from plate-like behavior to stagnant lid convection or to an intermediate regime. This sensitivity leaves open the possibility that Earth has not always operated in exactly the same way, and that plate tectonics itself may change character over time. The origin of individual plates also involves interactions between mechanical forces and chemical differentiation. As basaltic oceanic crust forms at spreading centers and then cools as it moves away, it becomes denser. Eventually at subduction zones, this dense lithosphere bends downward and sinks back into the mantle. This ongoing recycling helps maintain plate boundaries and drives motion. But the very first subduction event would have required pre-existing weaknesses in the early lithosphere, perhaps created by very large impacts or by strong mantle plumes rising from deep within the planet. Such plumes may have produced large volcanic plateaus and weakened the surrounding lithosphere, making it easier for parts of the shell to founder and initiate subduction. Once started, the process could become self-sustaining, with sinking slabs pulling on the plates and further breaking up the outer shell. In this view, plate tectonics is not a simple, inevitable outcome of planetary cooling, but a specific mode of behavior that began under particular conditions and may not last indefinitely. As Earth continues to cool and its internal heat budget declines, the style of convection and the strength of the lithosphere may again shift. The plates that now drift, collide and separate could slow and eventually lock into a more rigid configuration, reshaping the long-term evolution of continents and oceans. The present pattern of plates then is one phase in a possibly changing sequence, and the birth of plates from an earlier solid shell remains an active frontier in understanding how the planet came to have its current dynamic surface. Over geological time, the shifting plates of the lithosphere bring continents together and pull them apart so that the map of land and sea passes through very different configurations. At several points in Earth's history, most of the continents gather into a single large landmass, a supercontinent surrounded by a vast global ocean. One such configuration, known as Pangaea, forms hundreds of millions of years ago, and later breaks apart into fragments that drift to form the present continents. The idea that continents move and that they were once joined arises from several lines of evidence. The fit of continental margins is one of the most visually striking clues. The eastern coastline of South America and the western coastline of Africa show a broad geometric complement, especially when continental shelves are taken into account rather than only the present shorelines. Similar correspondences appear in other regions when deeper crustal structures and paleogeographic reconstructions are considered. Rock formations and mountain belts that now lie on different continents can be traced across oceans matching in age, composition, and deformation history. Fossil distribution supply further support. The remains of land-dwelling animals and plants that could not cross wide oceans unaided occur on multiple continents now separated by large distances. For instance, fossils of certain ancient reptiles and seed ferns appear in South America, Africa, India, and Antarctica, indicating that these regions were once connected in a common landmass. Glacial deposits also record former linkages. Striations and tillites from ancient ice sheets preserved in rocks now found near the equator align in patterns that make sense only when the continents are placed together in a different arrangement. These observations, combined with paleomagnetic data that indicate the past positions of continents relative to Earth's magnetic field, support the concept of Pangaea and its breakup through plate motion. Pangaea, however, is not the first nor the only supercontinent inferred from geological records. Earlier in the planet's history, other large continental assemblies such as Rodinia and Nuna, also called Columbia, are proposed based on correlations of old crustal blocks matching sequences of sedimentary rocks and ages of large igneous provinces. The exact shapes, sizes, and lifespans of these earlier supercontinents are less certain than those of Pangaea because the rocks that record them are older and more modified by later events. Nevertheless, patterns emerge that suggest a long-term rhythm in the way continents cluster and disperse. Some studies propose a supercontinent cycle with intervals of several 100 million years between successive assemblies. In this view, continental plates repeatedly converge to form a large landmass, which then breaks apart as new ocean basins open along rifts before the fragments eventually come together again in a new configuration. The drivers of this cycle connect directly to plate tectonics. As oceanic plates form at mid-ocean ridges and subduct at trenches, continents riding on them are carried along. Where subduction zones face each other on opposite sides of an ocean basin, the intervening oceanic crust is gradually consumed and the continents on either side converge. Collisions between continents create mountain belts and thickened crust as seen in the Himalayas and the ancient collision zones within Eurasia. During the assembly of a supercontinent, many such collisions occur, stitching together numerous smaller landmasses into one large block. Once formed, a supercontinent modifies the patterns of mantle convection beneath it. The thick insulating crust reduces heat loss from the mantle directly under the landmass, potentially leading to a warmer region beneath the supercontinent. Over time, this thermal anomaly may promote the formation of mantle plumes and widespread magmatism, which can weaken the overlying lithosphere. Large igneous provinces where vast volumes of basaltic magma erupt in relatively short geological intervals are often associated with the breakup of supercontinents. These magmatic events may initiate rifting, splitting the supercontinent into separate pieces that then drift apart as new ocean basins form between them. Yet the details of this feedback between plates and mantle are still being refined. It is not clear whether mantle convection patterns primarily drive the supercontinent cycle, or whether the changing arrangement of continents strongly reorganizes mantle flow. Seismic imaging of the deep mantle reveals large regions of anomalous structure near the core mantle boundary, sometimes described as superplume regions. These zones appear to be long-lived and may influence where supercontinents tend to assemble, suggesting a possible link between deep mantle structures and surface configurations. If certain areas of the deep mantle remain hotter and less dense for extended periods, convection currents might repeatedly carry continents toward those zones favoring supercontinent formation above them. Another layer of complexity arises from the role of oceans. When continents cluster together a single vast ocean often referred to as a panthalassa, type ocean can surround the supercontinent while smaller inland seas and marginal basins occupy the interior and edges. Ocean circulation patterns under such a configuration differ from those of a world with many separate ocean basins. The arrangement of land and sea affects climate-atmospheric circulation and the distribution of rainfall. During the time of Pangaea, large parts of the interior may have experienced extreme seasonal contrasts and arid conditions, while coastal regions and smaller basins supported different environments. As the supercontinent breaks apart, new coastlines form shallow continental shelves, expand and narrow seaways open, reshaping habitats for marine and terrestrial life. The fossil record shows pulses of diversification and extinction that coincide with major tectonic reorganizations, including supercontinent assembly and breakup, though many other factors also contribute. Despite the broad outline of the supercontinent cycle, significant uncertainties remain. The exact number of past supercontinents, their configurations, and the timing of their assembly and dispersal are still debated. For some proposed supercontinents, key links between crustal blocks are supported by limited or ambiguous data. Paleomagnetic reconstructions must correct for the wandering of the magnetic poles and for local structural tilts in rocks, and these corrections introduce uncertainties. Erosion metamorphism and later tectonism can erase or obscure critical evidence. As new data arrive from detailed mapping, radiometric dating, and geochemical analysis models of past continental arrangements are revised. Sometimes blocks thought to belong to one supercontinent are reassigned to another, or the positions of old cratons are shifted by thousands of kilometers relative to earlier interpretations. This evolving picture underscores how the story of vanished worlds is reconstructed from incomplete and partially altered records. The concept of a repeating supercontinent cycle also raises questions about regularity. If supercontinents form at roughly similar intervals, what sets this timescale? Some models suggest that it arises naturally from the characteristic scales of mantle convection and lithospheric strength. Others propose that the cycle may be more irregular, with some assemblies more complete and long-lived than others. It is also possible that in the earliest parts of Earth's history, when the mantle was hotter and the crust perhaps thinner, and more dynamic continental behavior did not follow the same patterns as in later eons. In that case, the familiar cycle inferred from Pangaea and its suggested predecessors might be a relatively recent mode of behavior rather than a universal rule. Looking forward, present plate motions imply that continents are still moving in ways that could lead to another supercontinent hundreds of millions of years in the future. Some scenarios place this future landmass near the current equator, while others cluster continents near one of the poles or assemble them around the Pacific basin as the present oceans continue to open and close. Each scenario arises from different assumptions about how plate boundaries will evolve, where new subduction zones will form, and how mantle convection will respond. Because these processes are complex and sensitive to changes that cannot be predicted in detail. So far ahead, the future map remains uncertain. What is clear is that the continents and oceans visible today occupy a single frame in a much longer sequence. Their past gatherings into supercontinents and their dispersals into separate land masses show that the crust is guided by deep forces that act over timescales far beyond human experience. The incomplete but growing record of these vanished configurations leaves open questions about how strongly deep mantle structures control surface maps, whether there are preferred patterns that repeat, and how many different kinds of supercontinent arrangements Earth has already hosted. Oceans as they exist today are closely tied to the places where plates move apart because new oceanic crust is created along long elevated underwater chains known as mid-ocean ridges. These ridges encircle the planet like seams, mostly hidden beneath kilometers of water, yet forming one of the most extensive geological features on Earth. At a divergent plate boundary, two plates move away from each other. The lithosphere stretches and thins, and the underlying warmer mantle rises to fill the gap. As it rises, the pressure on the mantle rock decreases, allowing some of it to melt, without a major increase in temperature, a process called decompression melting. The resulting magma, less dense than the surrounding solid rock, ascends through fractures and porous pathways, eventually reaching the base of the rigid plate or erupting on the seafloor. As this magma cools, it solidifies to form new oceanic crust, usually composed of basalt. Over time, repeated episodes of magmatic intrusion and eruption build a layered structure beneath the ridge with a sheeted complex of frozen magma conduits and thick piles of volcanic flows that spread away from the ridge axis. Surveys of the ocean floor using sonar mapping reveal that mid-ocean ridges are not flat expanses, but narrow elevated features with central rift valleys or crests, flanked by sloping flanks cut by numerous faults. The Mid-Atlantic Ridge, for example, runs roughly north to south between the Americas and the continents of Europe and Africa. It marks the boundary where plates on either side move apart, slowly widening the Atlantic Ocean. Similar ridges span the Pacific, Indian, and Southern Oceans together, forming a network that more than doubles the length of all mountain ranges on land. Along these ridges, the crust is youngest. As one moves away from the ridge axis, the crust becomes progressively older and thicker, and the seafloor deepens because the cooling plate becomes denser and sinks slightly into the mantle. Age dating of seafloor rocks combined with measurements of spreading rates shows a clear pattern, symmetric bands of progressively older crust on either side of the ridge. This pattern supports the concept of seafloor spreading, in which new crust forms at ridges and is transported outward, carrying the overlying ocean with it. An additional line of evidence comes from the magnetic properties of the basaltic crust. When basaltic lava cools iron-bearing minerals within, it records the direction of Earth's magnetic field at that time. Over Earth's history, the magnetic field has reversed many times, so that the positions of north and south magnetic poles have switched. These reversals are recorded in rocks on land and can be dated. When the magnetization of the ocean floor is measured, it reveals alternating bands of normal and reversed polarity running parallel to the ridge axes, forming a striking striped pattern. The widths of these stripes correspond to the durations of magnetic intervals, and the symmetry of the pattern on either side of a ridge provides a time-stamped record of seafloor spreading. The combined age and magnetic data from many ridges worldwide allow reconstruction of how ocean basins have opened over tens of millions of years. Despite this clear framework, several aspects of ridge dynamics remain open to investigation. Mid-ocean ridges do not all behave identically. Some segments are hot and volcanically active with frequent eruptions and robust magma chambers, while others appear cooler and more tectonically dominated with extensive faulting and less obvious magmatism. Spreading rates vary from place to place, with some ridges separating at only a few centimeters per year, and others at several times that rate. Faster spreading ridges tend to have smoother topography and narrower central rifts, while slow spreading ridges exhibit rugged terrain and deeply incised valleys. The reasons for these differences involve variations in mantle temperature composition and melt supply, but many details are still debated. Seismic studies beneath ridges show zones of partial melt in the upper mantle, but the exact geometry and connectivity of these melt regions are complex. Some images suggest that melt is focused in narrow columns directly beneath the ridge, while others point to broader regions of melt accumulation that may feed multiple ridge segments. Hydrothermal circulation adds another layer of complexity. Seawater penetrates down through cracks in the newly formed crust, heats up as it approaches underlying magma or hot rock, and rises back to the seafloor in hot springs. These hydrothermal vents, sometimes called black smokers, when they emit mineral-rich dark plumes, deposit sulfide minerals and support unique biological communities. The presence of such systems indicates that heat flow through the crust at ridges is not uniform but concentrated in channels where fluid circulation is intense. The distribution and variability of hydrothermal fields along ridges provide indirect clues about subsurface heat and magma patterns, yet many segments remain unmapped and unsampled, leaving gaps in the understanding of ridge-scale processes. The formation of new oceanic crust at ridges also raises broader questions about how mantle processes shape the long-term evolution of oceans. Basalt erupted at ridges has broadly similar compositions worldwide, yet subtle differences in trace elements and isotopes reveal that the mantle supplying melt is chemically heterogeneous. Some ridge segments overlie regions where deep mantle plumes approach the surface, such as near Iceland on the mid-Atlantic ridge. In these areas, the crust may be thicker and more magmatic, and the geochemical signatures carry hints of deeper sources. Elsewhere, ridges lack such plume influence and tap more depleted mantle. These variations suggest that the mantle beneath ridges is not a uniform layer, but a patchwork of domains with different histories of melting and mixing. Over long timescales, as oceanic plates move away from ridges and eventually subduct, they return altered material to the mantle, including crust that has interacted with seawater and sediments that have accumulated on the seafloor. This recycling introduces additional complexity into the chemical structure of the mantle. The patterns in ridge basalts thus encode information about cycles of creation and destruction that extend deep into the planet. Some anomalies in ridge behavior hint at processes not yet fully captured in models. In certain regions, for example, ridge segments appear to reorganize their positions over time, with transform faults lengthening or shortening, and ridge axes jumping laterally. These changes may reflect shifts in plate boundary forces or underlying mantle flow, but their timing and triggers are not always clear. In other cases, unexpected variations in crustal thickness along ridges suggest localized upwellings or downwellings in the mantle, beyond the simple picture of uniform passive upflow beneath a spreading center. Global compilations of ridge depth crustal structure and gravity anomalies show patterns that can be partially explained by known factors such as age, spreading rate, and mantle temperature, but residual variations remain. Such residuals may point to deeper mantle structures, long wavelength convective patterns, or inherited features in the lithosphere that deflect or focus melt. Oceans in this view are not merely water-filled depressions, but active parts of a system in which the sea floor itself is continually created, modified, and destroyed. The mid-ocean ridges, though hidden from direct human experience by overlying water, mark the lines where new ocean basins begin. Their behavior recorded in topography, magnetic stripes and chemical fingerprints shows how plate divergence sculpts both the solid Earth and the shape of the global ocean. Yet the detailed connections between mantle convection, ridge volcanism, hydrothermal systems, and long-term ocean evolution remain incompletely understood, leaving open questions about how regular or erratic the creation of new seafloor has been through time, and how subtle shifts in the deep interior may be recorded in the fabric of the oceanic crust. At convergent plate boundaries, the relentless motion of the lithosphere brings plates together, forcing one to descend into the mantle, or causing them to crumple and thicken, and in doing so builds some of Earth's most dramatic surface features. Where dense oceanic lithosphere meets less dense continental lithosphere, the oceanic plate typically bends downward and begins to sink beneath the continent in a process known as subduction. This bending creates a deep ocean trench at the surface, a long, narrow depression that can reach depths of many thousands of meters below sea level. On the overriding plate, a chain of volcanoes and deformed rocks commonly develops, forming an arc that may stand as an island chain or a coastal mountain belt. The combination of trench subducting slab and volcanic arc is a hallmark of ocean-continent convergence. Famous examples include the Andean margin of South America and island arcs in the Pacific. Where two oceanic plates converge, one usually subducts beneath the other, creating a similar arrangement of trench and volcanic arc in an oceanic setting. When two buoyant continental plates collide after the oceanic lithosphere between them has been consumed, neither plate easily sinks. Instead, the crust thickens and uplifts, producing extensive mountain ranges such as the Himalayas, often built upon earlier subduction-related structures. These convergent settings concentrate some of the strongest earthquakes and most explosive volcanic eruptions known, yet their detailed behavior shows patterns that are not yet fully understood. Seismic networks record earthquakes along subduction zones at a wide range of depths, from shallow events near the trench to deep focus earthquakes hundreds of kilometers beneath the surface. The distribution of these earthquakes outlines the descending slab as it plunges into the mantle, tracing a zone sometimes called a Wadati-Benioff zone. The angle at which the slab dips, the depth to which earthquakes occur, and the total width of the seismically active region vary from one subduction zone to another. In some places the slab descends steeply, while in others it flattens out beneath the overriding plate for hundreds of kilometers before continuing its descent. These differences influence the pattern of volcanism and deformation above, but their causes are complex. Factors such as the age and thickness of the subducting plate, the rate of convergence, the presence of sediments, and the temperature of the mantle all play roles, yet the full set of controls is still being explored. Deep focus earthquakes in particular pose a continuing puzzle. At depths greater than a few tens of kilometers, rocks are generally expected to deform in a ductile manner, flowing rather than fracturing brittly. Nevertheless, earthquakes with significant magnitudes occur at depths reaching several hundreds of kilometers within subducting slabs. Various mechanisms have been proposed to explain these events, including transformations of minerals to denser structures that release stored elastic energy, or local instabilities related to phase changes and dehydration reactions. Laboratory experiments and theoretical models show that such processes are plausible, but direct observations at such depths are not possible, and each deep earthquake sequence offers new details that must be reconciled with existing ideas. Some subduction zones are also marked by gaps in shallow seismic activity, along the trench regions where fewer earthquakes occur over decades despite ongoing plate convergence. These so-called seismic gaps may represent areas where strain is accumulating for a future large earthquake, or they may indicate zones where slip occurs more quietly through a process known as slow slip, in which the plates move relative to each other over days to months without generating strong seismic waves. Slow slip events have been detected by precise geodetic measurements, revealing episodes of motion that would otherwise go unnoticed. They sometimes coincide with swarms of small low-frequency tremors deeper along the plate interface. The occurrence, timing, and extent of slow slip vary from one subduction margin to another, and the relationship between slow slip and large damaging earthquakes remains an area of active research. Some major earthquakes have been preceded or accompanied by slow slip, suggesting a possible link, but in other cases slow slip appears to relieve stress without leading to a catastrophic rupture. The variability hints at a complex frictional landscape along the plate boundary, where patches of the interface behave differently, depending on pressure, temperature, fluid content, and rock type. Subduction zones also host large-scale topographic features that challenge simple models. Not all trenches are equally deep, and not all arcs produce the same volumes of magma. In some regions, broad plateaus or underwater mountain chains on the subducting plate enter the trench and change the style of deformation. These features may temporarily jam subduction, alter the dip of the slab, or create areas of uplift and increase seismicity on the overriding plate. In other areas, so-called flat slab segments carry the subducting plate horizontally beneath the continent for great distances before it descends more steeply. Above these flat slabs, volcanic activity may be reduced or shifted landward, while the crust experiences unusual patterns of thickening and uplift. Geophysical imaging using seismic tomography and gravity data reveals that some subducted slabs penetrate deep into the lower mantle, while others seem to stall or flatten at mid-mantle depths. The reasons for these differences involve the density and temperature structure of the mantle, and the evolving buoyancy of the slab as it descends, but details are still uncertain. The long-term fate of slabs that sink to the lowermost mantle and their influence on deep mantle structures and convection patterns remain important open questions. The chemical exchanges at subduction zones add further intrigue. As the oceanic plate descends, sediments altered oceanic crust and hydrated mantle. Minerals carry water and other volatile components into the mantle. At certain depths, these materials release fluids that rise into the overlying mantle wedge, lowering its melting point and generating magmas that feed arc volcanism. The compositions of volcanic rocks erupted in arcs reflect this process, showing signatures of recycled crustal and sedimentary material. Over billions of years, subduction has likely returned vast amounts of surface-derived material into the interior, while volcanic arcs have transported mantle-derived magmas and gases back to the surface. This deep recycling connects plate tectonics to long-term cycles of elements such as carbon and water, with implications for climate and habitability. Yet not all subduction zones appear equally efficient at recycling, and some geochemical traces hint at reservoirs in the deep mantle that retain ancient signatures, possibly from early episodes of subduction or from material that never mixed thoroughly. The balance between efficient mixing and long-lived heterogeneity is a subject of ongoing investigation. Continental collision zones where subduction has effectively ceased and thickened, crust dominates present their own uncertainties. The Himalayas and the Tibetan Plateau, for example, rise above a region where an earlier oceanic plate once sank, and where parts of the continental lithosphere now overlap and crumple. The crust there is unusually thick, and the plateau stands at high elevation over a broad area. Various models propose different combinations of crustal shortening, lower crustal flow, and delamination, in which dense lower lithosphere peels away and sinks to explain the observed features. Seismic images provide some constraints on the geometry of the colliding plates, but interpretations differ, and the ongoing uplift and deformation suggest that the system has not reached a simple equilibrium. Similar complexities appear in older mountain belts that have long since eroded to lower elevations, where fossils of ancient collisions are preserved in high-grade metamorphic rocks and deformed structures. Together, these observations show that convergent boundaries are not a single type of feature, but a spectrum of behaviors shaped by many interacting factors. Subduction and collision create the highest mountains and deepest trenches, concentrating tectonic energy along relatively narrow belts. They play a central role in building continents, recycling oceanic crust, and driving some of the most hazardous earthquakes and eruptions. At the same time, variations in slab geometry, seismic behavior, magmatism and geochemical signatures reveal a system that is sensitive to initial conditions and evolving properties. This sensitivity means that even as the broad outline of convergent plate tectonics is understood, many details remain unresolved, leaving open questions about how predictable these systems are, how they respond to changes in plate motions and mantle convection, and how their deep processes shape the long-term evolution of continents and oceans. Not all plate boundaries involve plates moving toward or away from each other. At many margins, plates slide past one another horizontally along features known as transform boundaries. Here, the main relative motion is lateral, with little or no creation or destruction of crust. The contact surfaces where this motion localizes are long faults that can extend for hundreds or even thousands of kilometers. On land, these transform faults are sometimes marked by linear valleys, offset streams, and sudden changes in landscape, while on the ocean floor they cut across mid-ocean ridges, offsetting ridge segments and linking different spreading centers. Together, these structures allow the curved surface of Earth to accommodate complex patterns of plate motion without tearing or overlapping in ways that would open gaps or create large overlaps. The physics of sliding faults, although studied for decades, still contains open questions. At a basic level, as plates move, stress builds along the boundary where they're locked together by friction. When the stress exceeds the strength of the fault, a rapid slip event occurs, releasing energy as seismic waves and producing an earthquake. After the rupture, the fault is briefly closer to equilibrium, but as plate motion continues, stress begins to build again. This simple stick-slip picture explains why earthquakes tend to recur on certain faults, and why they involve sudden movements preceded and followed by quieter intervals. However, detailed observations show that real faults host a wide range of behaviors that depart from this simple pattern. Major transform faults on land, such as the well-studied example that runs through California, are segmented. Different parts of the fault move at different long-term rates and show different seismic styles. Some segments are locked for long periods and then rupture in large earthquakes. Others exhibit steady creep, moving slowly and almost continuously, without generating strong shaking. Between these extremes, there are regions where slow slip events, clusters of small earthquakes, and occasional moderate events coexist. High-resolution measurements from dense seismic networks and satellite-based ground deformation studies reveal that even along a single fault slip may occur in patches, with some areas repeatedly breaking in similar small earthquakes, and others remaining quiet for long intervals. The reasons for these variations include differences in rock type, temperature, fluid pressure, and fault roughness, but their combined effect is difficult to model in detail. In the ocean's transform faults, offsetting mid-ocean ridges generally produce moderate earthquakes and lack the high relief of continental counterparts, yet they also show variations in activity that are not fully explained. Some ridge transform systems appear to reorganize over time with individual fault segments, lengthening, shortening, or abandoning one another as spreading patterns change. The link between these reorganizations and deeper mantle dynamics or changes in plate-driving forces is still being explored. Another layer of complexity lies in the frictional properties of fault rocks. Laboratory experiments on rock samples sheared under controlled conditions show that friction can depend on sliding velocity, temperature, and the presence of fluids, and that under some conditions faults weaken more as they begin to slip, encouraging unstable seismic failure. Under other conditions, faults tend to strengthen during slip-promoting stable creep. However, extrapolating laboratory results, which operate over centimeter scales and short times, to faults that extend for many kilometers and slip over seconds to centuries is challenging. Boreholes drilled into active faults provide in situ measurements of temperature, stress, and material properties, and have recovered samples of fault gouge, the finely crushed material that fills fault zones. Some results suggest that the effective frictional resistance on major faults during earthquakes may be lower than expected, raising questions about what processes such as the presence of pressurized fluids or dynamic weakening mechanisms reduce friction during rapid slip. Earthquake records reveal additional features that invite further study. In some regions, sequences of moderate earthquakes migrate along a fault at speeds much slower than seismic wave velocities, indicating that the underlying slip front propagates gradually. In other cases, small repeating earthquakes occur at nearly the same location with similar waveforms over months or years, suggesting that a small patch of the fault repeatedly fails as stress accumulates. These repeating events can act as natural probes of fault loading and slip, but their occurrence is not uniform along all faults. Some segments produce many such sequences, while others do not, even where overall conditions appear comparable. This patchiness hints at subtle heterogeneity in fault zone conditions. Transform faults also show intriguing connections to distant events. There are documented cases in which large earthquakes in one region of the world are followed by small increases in seismicity along faults thousands of kilometers away, sometimes within minutes to hours. The passing seismic waves from the distant event appear to perturb stresses or fluid pressures enough to trigger marginally stable patches into slipping. This dynamic triggering does not cause major earthquakes directly, but it reveals that faults can be sensitive to relatively small changes in stress if they are already close to failure. The extent to which such remote influences modulate the long-term earthquake cycle is uncertain, yet they demonstrate that fault systems are not entirely isolated. Tidal forces from the gravitational pull of the Moon and Sun also produce small periodic stresses in Earth's crust. In some regions, careful statistical studies have found weak correlations between tides and the timing of certain types of earthquakes or slow slip events, especially in environments where fluid pressures are high and effective normal stresses on faults are low. These correlations do not imply simple tidal control of earthquakes, but they indicate that tiny predictable stress oscillations can sometimes influence fault behavior when conditions are favorable. This sensitivity underscores that faults operate near thresholds where small perturbations can matter. Along some plate boundaries, particularly in subduction transition zones that gradually merge into transform-style motion, slow slip events and non-volcanic tremor occur in semi-regular patterns. Geodetic observations record episodes when parts of a fault slip over days to weeks without generating strong shaking, accompanied by low-frequency seismic signals that differ from typical earthquakes. These phenomena blur the boundary between stable creep and abrupt rupture. They also suggest that the spectrum of fault slip includes modes that transfer significant amounts of plate motion without causing damaging earthquakes, yet may still affect the stress distribution and thus the probability of future seismic events. How these slow and silent processes interact with the parts of faults that host large earthquakes is an open area of research. Transform boundaries influence the arrangement of continents and oceans in ways that are more subtle than those of spreading ridges and subduction zones, but they remain essential elements of the plate tectonic system. On the seafloor, they connect segments of mid-ocean ridges, offset magma supply, and create small basins and steps that shape the detailed topography of ocean basins. On land, they can mark the boundaries between different terrains and control the orientation of basins' ranges and sedimentary deposits. Over long periods, repeated earthquakes, uplift and subsidence along transform margins accumulate into noticeable landscape changes, guiding river courses and influencing sediment delivery to the oceans. The distribution of major transform faults on Earth also raises comparative questions. Other planets and moons show evidence of strike-slip motion in certain regions, but the organized network of long transform faults, linked to a global system of spreading and subduction, appears unique to Earth. This uniqueness may reflect the particular balance of plate motion's lithospheric strength and internal heat that maintains the present plate configuration. It may also tie into the presence of oceans and a hydrologic cycle that modulates fault strength through fluid pressures. The way sliding faults distribute and concentrate stress store and release elastic energy and respond to small perturbations therefore remains a focus of investigation, with implications not only for understanding hazardous earthquakes, but also for interpreting the long-term evolution of plate boundaries. Despite the wealth of modern data from seismometers, satellites, and boreholes, many aspects of transform fault behavior evade precise prediction. Earthquakes vary in size, location, and timing in ways that reflect a complex interplay of conditions on and around the fault. The ongoing effort to link observable fault properties to earthquake statistics, to integrate laboratory and field observations across scales, and to incorporate slow and silent slip modes into comprehensive models, continues to reveal both progress and gaps. In this complexity, transform boundaries illustrate how even a seemingly simple plate motion, sliding sideways rather than colliding or separating, can generate a rich spectrum of phenomena that connect the deep driving forces of plate tectonics to sudden surface-level changes in the crust that hosts continents and borders oceans. Water covers most of Earth's surface, filling the ocean basins that form as plates pull apart and new crust cools and sinks, and flooding continental margins where the lithosphere flexes under changing loads. This water is not just a passive layer above the solid planet. It interacts with rocks, minerals, and gases cycling between surface and interior, and influencing how plate tectonics operates. At the same time, plate motions help regulate the long-term distribution of water between oceans, atmosphere, and crust, and shape the conditions that allow complex life to persist over hundreds of millions of years. The link between water life and moving continents is therefore one of mutual influence, rather than a simple one-way control. Liquid water on the surface participates in the hydrologic cycle, where evaporation, condensation, precipitation, runoff, and infiltration move it through atmosphere, rivers, glaciers, soils, and aquifers. As rain and snow fall on continents, they weather rocks, breaking down minerals and transporting dissolved ions and sediments to the oceans. Chemical weathering of silicate rocks consumes carbon dioxide from the atmosphere and produces bicarbonate ions that eventually form carbonate minerals in marine sediments. Over long timescales, this weathering and burial process acts as a sink for carbon dioxide, helping regulate atmospheric composition and global temperature. The rate of weathering depends on factors such as temperature, rainfall, vegetation cover, and the area and elevation of exposed land. Plate tectonics influences all of these by building mountain ranges, shaping continental outlines, and controlling the positions of landmasses relative to climatic zones. In turn, climate and life influence how efficiently weathering operates, feeding back into the carbon cycle. Beneath the oceans, seawater circulates through the upper parts of the oceanic crust, particularly near mid-ocean ridges and other volcanic centers. As it descends along fractures and heats up, it reacts with basaltic rocks, altering their mineralogy and incorporating elements such as magnesium and calcium, while releasing others back into the ocean. This hydrothermal alteration hydrates the crust and transfers heat and chemical components between lithosphere and seawater. When this altered crust eventually reaches a subduction zone, some of the bound water and volatiles are carried into the mantle, where they are released at depth and contribute to melting and arc volcanism. In this way, plate tectonics continuously cycles water into and out of the interior. Measurements from deep-sea drilling programs and ocean bottom observatories, coordinated by international consortia and supported by agencies including national geological surveys and space-based remote sensing bodies such as NASA and the European Space Agency, help quantify these fluxes by mapping sediment thickness, crustal structure, and heat flow. Although estimates vary, it is clear that over billions of years, significant amounts of water have been transported into the mantle and out again. The presence of water in the mantle changes its behavior. Even small amounts of water dissolved in minerals lower the melting point and reduce the effective viscosity of rocks, making it easier for the mantle to flow and for magma to form. This suggests a feedback plate tectonics promotes water cycling into the mantle, and that water in turn may help keep the mantle convecting and the lithosphere weak enough to maintain plate motions. Planets with little or no surface water may lack this feedback, leading to stronger lithospheres that resist breaking into plates. At the same time, the total amount of water in the oceans is influenced by the balance between water input from volcanic outgassing and water loss to the deep interior or space. Models of this balance remain uncertain, but geological evidence indicates that liquid water has persisted on the surface for most of Earth's history, even when the young sun shone less brightly than it does today. This so-called faint young sun problem has been addressed by invoking higher levels of greenhouse gases, in the past increased geothermal heat flux, or different cloud and ice cover, but plate tectonics also plays a role. By regulating carbon dioxide through weathering and volcanic degassing, moving continents into and out of equatorial regions, and altering ocean gates that control circulation plate motions, contribute to maintaining a climate that allows water to remain liquid over immense spans of time. The arrangement of continents strongly affects ocean currents and therefore climate. When continents cluster near the poles, large ice sheets can grow, raising the albedo of the planet and cooling global temperatures. When continents scatter and open wide equatorial seaways, warm currents may flow more freely, redistributing heat and moderating temperature gradients. During periods when supercontinents exist, interior regions far from the sea can become dry and subject to extreme seasonal temperature swings, while newly formed rift basins and epicontinental seas along divergent margins create shallow marine environments rich in nutrients and sunlight. As plate motions change these arrangements, marine and terrestrial ecosystems track shifting coastlines, mountain barriers, and climatic zones. Paleoclimate records preserved in sediment cores, ice layers, and fossil assemblages show that many major shifts in climate and biodiversity coincide with tectonic reorganizations, though other factors such as impacts and variations in orbital parameters also contribute. Some of the most dramatic episodes in Earth's climate history, such as intervals when ice may have extended to low latitudes, have been linked to particular continental configurations and weathering regimes. When continents aggregate near the equator, enhanced weathering in warm, wet conditions can draw down atmospheric carbon dioxide, potentially pushing the climate toward extensive glaciation. As ice advances, chemical weathering may slow, allowing volcanic outgassing to rebuild greenhouse gas levels and eventually warm the planet again. In such scenarios, plate tectonics sets the stage for extreme climate swings, while the carbon cycle and water cycle provide the mechanisms. Life interacts with these processes in multiple ways. Photosynthetic organisms in oceans and on land influence atmospheric composition by consuming carbon dioxide and releasing oxygen. Roots and soil biota enhance weathering by breaking up rocks and producing organic acids. Carbon produced by biological activity is buried in sediments, altering the long-term carbon budget. The distribution of life across the planet responds to the positions of continents, the depth and shape of ocean basins, and the pattern of upwelling and nutrient delivery controlled by plate tectonic features such as mid-ocean ridges, continental shelves, and subduction-related volcanic arcs. Over time, the evolution of life and the evolution of continents and oceans become intertwined. Some researchers have suggested that the emergence and spread of land plants, for example, increased weathering rates and contributed to shifts in climate that may have influenced tectonic and erosional patterns. Conversely, the uplift of large mountain ranges creates new habitats and environmental gradients that can accelerate biological diversification. These interactions suggest that on Earth, plate tectonics, climate and life form a coupled system with feedbacks operating over a wide range of timescales. Despite this general picture, many details remain unsettled. The exact timing and magnitude of water fluxes into and out of the mantle are still being refined, as are estimates of how much water resides in deep reservoirs compared with the surface oceans. High-pressure experiments and seismic studies hint that significant amounts of water may be stored in nominally anhydrous minerals in the mantle transition zone and lower mantle, but the distribution and mobility of this water are not well constrained. If large, deep reservoirs exist, they may buffer surface ocean volumes over long periods, affecting sea level and the stability of climates suitable for life. Likewise, the strength of feedbacks between weathering atmospheric carbon dioxide and temperature depends on the availability of fresh rock surfaces, which in turn depends on tectonic uplift erosion and the presence of vegetation. Quantifying these feedbacks is challenging, and different models produce different degrees of climate stability. Comparisons with other planets deepen the mystery. Mars shows signs of ancient liquid water flows and possible lakes and seas, but its present thin atmosphere and cold dry surface suggest that any early climate regulation did not persist. Without active plate tectonics, weathering and volcanic degassing on Mars may have followed different trajectories, allowing greenhouse gases to escape or be sequestered without a balancing feedback. Venus, with its thick hot atmosphere and possible history of past oceans, presents another extreme where a lack of present-day plate tectonics and a different style of volcanic and tectonic activity may have contributed to a runaway greenhouse state. These contrasting examples raise the question of how rare Earth's combination of long-lived surface water, active plate tectonics, and complex life might be. Observations of exoplanets around other stars, including those in so-called habitable zones, where temperatures could allow liquid water at another dimension. For some of these distant worlds, measured densities, sizes, and orbital properties suggest that they might possess rocky surfaces and substantial water inventories. Without direct observations of their surfaces, it is unknown whether they host plate tectonics or some other mode of heat loss. Theoretical studies explore how planetary mass composition, internal heat, and water content could influence the likelihood of plate tectonics, but results vary. Some scenarios suggest that more massive rocky planets might more easily sustain plate tectonics, while others indicate that higher gravity and thicker lithospheres could instead favor stagnant lids. The presence of deep oceans might lubricate plates and promote mobility, or might create pressures on the seafloor that inhibit subduction. These uncertainties leave open the question of whether plate tectonics is a common outcome among water-bearing worlds or a relatively rare feature. On Earth, the observable result of this interplay is a planet where continents drift across latitudes, oceans open and close, climates shift, and life adapts and evolves. The coevolution of water life and tectonics has produced a distinctive environment in which long-term habitability has been maintained despite changes in solar output and intermittent global crises. Yet because only fragments of the deep past are preserved in rocks, and because other planets cannot yet be examined in comparable detail, the extent to which each factor depends on the others remains unclear. Whether plate tectonics is required for complex life, how strongly life modifies tectonic and climatic processes, and how stable the current arrangement of oceans and continents truly is over the longest timescales are questions that continue to drive research at the intersection of geology, climatology, and astrobiology. Deep within Earth, below the level where subducting slabs can be clearly traced, and far beneath the base of the lithospheric plate's mantle, convection patterns and structures become less accessible to direct observation yet their signatures appear in several types of data that reach the surface. One of the most visible surface expressions of deep mantle processes is the presence of hotspots and volcanic chains that do not fit neatly into the framework of plate boundaries. These regions, such as the volcanic islands in the central Pacific or the large igneous province that underlies parts of Iceland, show long-lived focused magmatism that persists as plates move over them. The hotspot hypothesis proposes that such features are fed by narrow mantle plumes, columns of relatively hot material rising from great depths, possibly from near the core mantle boundary. As a plate drifts across one of these upwellings, a chain of volcanoes forms with older extinct edifices trailing in the direction of plate motion, and younger, more active centers located above the current position of the plume. The linear island and seamount chains in some ocean basins with age progressions along their length provide support for this picture. Yet even here the details are more complex than simple conceptual diagrams suggest. Seismic imaging of the mantle beneath hot spots has revealed low-velocity regions that may correspond to hotter, possibly partially molten material. In some cases, such anomalies appear to extend to depths of several hundred kilometers, and in a few cases hints of even deeper connections have been reported. However, seismic resolution decreases with depth, and images are influenced by the distribution of earthquakes and seismometers, which is uneven across the globe. Different studies sometimes produce differing models for the same region, and whether many hotspots are truly rooted in the lowermost mantle or represent shallower upwellings linked to local features remains under discussion. The shapes of volcanic chains themselves can also deviate from simple expectations. Some show bends or kinks that reflect changes in plate motion, but others display irregularities in age progression or magma production rates. These variations suggest that plume strength composition or interaction with surrounding mantle flow can change over time. Numerical simulations of mantle convection that include buoyant plumes rising from the core mantle boundary can reproduce some aspects of hotspot behavior, such as broad swell regions around major plumes and long narrow upwellings. But matching all observed details remains a challenge. At the base of the mantle, just above the liquid outer core, seismic studies have identified two vast regions where seismic waves travel more slowly than in surrounding material. These large low-shear velocity provinces, one beneath parts of Africa and the Atlantic and the other beneath the central Pacific, have irregular shapes and extend upward several hundred kilometers into the mantle. Their exact composition, temperature and origin are not yet known. Some models interpret them as regions of hotter-than-average mantle, perhaps enriched in iron or other components that are less dense at high temperatures, but may have complex buoyancy properties. Others suggest that they could be accumulations of subducted oceanic crust or chemically distinct domains that have survived mixing over billions of years. Smaller, very low-velocity patches, sometimes called ultra-low-velocity zones, occur at the edges or within these larger provinces. These zones may represent partially molten material or even denser iron-rich layers, but their small size and deep position make them difficult to characterize. The presence of these anomalous structures at the base of the mantle raises questions about how they influence and are influenced by the global pattern of convection. Some researchers propose that the large low-velocity provinces act as anchors for upwelling plumes, with hot columns rising preferentially from their edges or tops. This could explain why some major hotspot clusters appear to lie above the margins of these deep structures. If true, this would represent a connection between the deepest parts of the mantle and the distribution of long-lived volcanism at the surface. However, not all hotspots fit this pattern, and the relationships may be more varied. The long-term stability of the large low-velocity provinces also remains under debate. Do they persist in roughly the same places for most of Earth's history, or do they drift and deform over hundreds of millions of years, reshaped by the slow overturning of the mantle and the influx of sinking slabs? Some paleogeographic reconstructions attempt to align ancient large igneous provinces, particularly those associated with supercontinent breakup, with the projected past positions of these deep structures. In some cases, the correspondence is suggestive, hinting that deep mantle features may maintain a degree of spatial coherence and influence where major upwellings reach the surface. Yet the uncertainties in both mantle imaging and past plate positions are significant, and it remains possible that the apparent alignments are partly coincidental. Beyond their role in feeding plumes, deep mantle anomalies may affect how subducting slabs sink and spread. Tomographic models show that in some regions slabs penetrate through the boundary between upper and lower mantle, and appear to pool or deflect around the large low-velocity provinces. In other regions, slabs seem to flatten or stagnate at mid-mantle depths, suggesting that changes in mineral phases or viscosity create barriers to smooth descent. These patterns imply that the mantle is not a uniform convecting shell, but a stratified chemically and rheologically complex system. The amount of heat transferred from the core into the mantle may vary regionally, altering convection strength above different parts of the core mantle boundary. This variation could in turn modulate plate driving forces at the surface, adding a slow, deep component to the evolution of plate configurations over time. Another observable signal from the deep interior comes from changes in Earth's rotation and gravity field. As mass redistributes within the mantle through convection and subduction, and as core flow evolves, the planet's moment of inertia changes slightly. Modern satellite missions measure tiny variations in gravity and rotation parameters with high precision, revealing patterns that when modelled can be related to flows within the mantle and outer core. While much of this variation is due to surface and near-surface processes such as ice mass changes and ocean circulation, a component arises from deeper, slower processes. Decoding this signal requires separating overlapping effects, but it offers a complementary window into the long-term stirring of the interior. Deep mantle structures also intersect with the history of Earth's magnetic field. The geodynamo in the outer core depends on patterns of heat loss into the overlying mantle. If the large low-velocity provinces alter how heat escapes from the core, they may influence the vigor and symmetry of core convection. Some studies suggest that the geographic distribution of magnetic field features averaged over long times may reflect this influence, with certain longitudes more prone to specific magnetic structures. Over millions of years, the frequency and character of geomagnetic reversals may also be modulated by how core flow's interaction with the lower mantle evolves. The evidence for such connections remains tentative, relying on statistical relationships and modelling rather than direct observation, but it points to a deep coupling between mantle and core that reaches all the way to the magnetic shield that extends into space. Despite these insights, many aspects of the deep mantle remain poorly constrained. Seismic imaging has limited resolution and is more sensitive in regions with dense earthquake and station coverage. In some oceanic and polar regions, data are sparse, leaving large volumes of the mantle less well imaged. Different inversion methods and parameter choices can produce different pictures of the same region, raising the question of how robust specific features are. Some apparent structures may partly reflect artifacts of the modelling process, while real features may be blurred or misplaced. Laboratory experiments on minerals at the pressures and temperatures of the lowermost mantle suggest that unexpected phase transitions, changes in compressibility, or the presence of minor components could alter seismic wave speeds in ways that complicate interpretations. The range of possible compositions and structures in these conditions is large, and the path from seismic velocity to physical state is indirect. Numerical models of whole mantle convection that attempt to incorporate realistic rheology's phase changes and compositional variations must also make approximations. Computational limits require compromises between resolution and the complexity of physics that can be included. As a result, there is no single definitive model of deep mantle flow. Instead, there is a suite of models that explore different assumptions and emergent behaviors. Some produce long-lived stable, large low-velocity provinces and focused plumes that reach the surface near their edges. Others show more chaotic reorganization of deep structures over time. In many cases, the same basic input parameters can give rise to different convective patterns depending on initial conditions. This sensitivity means that even if the general ingredients are known, the exact history of Earth's deep mantle may be difficult to reconstruct. The connection between deep signals and the creation and evolution of continents and oceans therefore remains partly speculative. Certain broad trends are clear subduction, carries surface material deep into the mantle. Plumes and upwellings bring deep material and heat back toward the surface, and long-term differences in mantle structure influence where and how these processes occur. Yet the details of how specific deep anomalies relate to the timing of supercontinent breakups, the formation of new ocean basins, or the growth of particular continental regions are not firmly established. The patterns in the available data hint at a planet whose interior retains memory over billions of years, with deep structures that guide surface tectonics, but the extent and nature of that memory are uncertain. Ongoing and future efforts, including more densely distributed seismic networks on land and sea, improved laboratory measurements at extreme conditions, and more advanced computational models aim to sharpen the picture. For now, the deep mantle remains a partially resolved landscape of rising and sinking material, chemically distinct domains and thermal anomalies whose influences are traced indirectly in hotspot tracks, gravity anomalies, and subtle variations in seismic wave speeds. Through these signals, a connection is maintained between the hidden base of the mantle and the ever-changing pattern of continents and oceans at the surface, suggesting that the familiar geography of the present is linked through complex and still not fully deciphered pathways to structures and motions thousands of kilometers below. The present pattern of continents and oceans, with the Atlantic slowly widening the Pacific, framed by long arcs of subduction zones, and Antarctica isolated at the southern pole, represents only one stage in an ongoing reorganization of Earth's surface. Satellite measurements of plate motions show that major plates continue to move at rates of a few centimeters per year, and when these vectors are projected forward over tens to hundreds of millions of years, they outline possible future configurations of land and sea. Several models of this future evolution have been proposed, each depending on assumptions about how existing plate boundaries will persist or change, and where new subduction zones might form. In one scenario, the Americas continue to drift westward until they collide with East Asia, closing much of the Pacific and assembling a new supercontinent in the northern hemisphere. In another, the Atlantic begins to close as subduction initiates along its margins, drawing Africa and the Americas back together near the equator. Other models cluster continents around the present position of the Pacific basin, or around a different pole. Each of these hypothetical supercontinents would be surrounded by a global ocean, or accompanied by secondary basins, much as earlier supercontinents were. While these possibilities provide useful frameworks for thinking about the future, they are not firm predictions. The initiation of new subduction zones, the shifting of existing ones, and the possible reconfiguration of transform and ridge systems all depend on processes that are hard to forecast in detail so far ahead. The long-term pattern of mantle convection influenced by the slow sinking of slabs and the rising of plumes from the deep mantle may also reorganize in ways that are not simply extrapolations of present behavior. Thus, the exact future map remains uncertain, but the underlying message is that continents are expected to keep moving, and that supercontinent assembly and breakup are likely to continue as long as plate tectonics operates. The persistence of plate tectonics itself is another open question. As Earth gradually loses internal heat, the vigor of mantle convection will decline, and the strength of the lithosphere may change. If the lithosphere becomes too strong relative to the driving stresses from the mantle plate, motions could slow and eventually enter a stagnant lid regime in which the outer shell moves as a single unit, with most heat loss occurring through conduction and episodic volcanism, rather than continuous plate recycling. Such a transition might resemble the inferred histories of planets like Mars or Venus, where large volcanic and tectonic events have occurred without evidence of long-lived globally coherent plate systems. On the other hand, continued water cycling into the mantle and ongoing weakening of plate boundaries could maintain plate tectonics for a very long time, even as overall heat flow declines. Estimates of how long plate tectonics can continue range widely, depending on assumptions about mantle rheology, heat production, and the efficiency of convective cooling. Current models suggest that there is no immediate threat to global plate mobility on human or even civilizational timescales, but over billions of years the regime could shift. The timing and character of any such change are not yet well constrained, adding a long-range dimension to the mystery of how continents and oceans will ultimately evolve. Even within the current tectonic regime, the detailed responses of plates' boundaries and the deep interior to gradual changes in driving forces remain topics of investigation. For example, if the rate of subduction in certain regions slows or accelerates, how will this affect the distribution of volcanic activity, the growth or decay of mountain belts, and the evolution of ocean basins, if the large low-velocity provinces at the base of the mantle inferred from seismic studies reorganize or reshape? Will this lead to shifts in where major mantle plumes rise and where future large igneous provinces may erupt? These questions connect deep mantle dynamics, which operate over hundreds of millions of years, to surface processes that can restructure continents and oceans. The geological record contains hints of such linkages in the clustering of large magmatic events, in pulses of mountain building, and in changes in the style of plate boundaries, but the cause and effect relationships are not always clear. Decoding these signals requires integrating data from many disciplines, including seismology, geodynamics, geochemistry, and sedimentology, and even then the picture remains incomplete. The relationship between plate tectonics and Earth's long-term climate adds another layer of uncertainty. As continents move, they alter ocean circulation patterns, mountain building, and the distribution of land across latitudes, influencing weathering rates and the carbon cycle. Future supercontinents may present different climatic challenges than those of the present world, with large interior deserts, altered monsoon systems, or extended periods of glaciation depending on their positions relative to the poles and equator. Over very long timescales, increasing solar luminosity will tend to warm Earth, potentially driving changes in the efficiency of weathering feedbacks and in the capacity of plate tectonics to regulate atmospheric greenhouse gases. At some point, this balance may shift in ways that cause the loss of stable surface oceans even if plate motions continue. The exact timing and interplay of these effects remain uncertain, but they underscore that the evolution of continents and oceans is intertwined with the evolution of climate and habitability. Observations of other planets and exoplanets offer external perspectives, but also increase the scope of unknowns. Within the solar system, Earth stands out as the only planet with both abundant surface water and clear evidence of active plate tectonics. Mars preserves relics of ancient water-related erosion and possible transient lakes, but no present-day plate system. Venus displays a young surface dominated by volcanic and tectonic features that suggest intense, possibly episodic resurfacing, yet no clear signs of spreading ridges or subduction trenches. These contrasts highlight that plate tectonics is not an inevitable outcome of planetary formation. Among exoplanets, some rocky worlds orbit in zones where liquid water could exist at the surface, and their sizes and densities suggest that they might host significant oceans. However, their internal structures, heat budgets, and lithospheric strengths are not directly measurable. Whether any of them operate under a plate tectonic regime similar to that of Earth, or whether they follow different paths such as stagnant lids, episodic overturn, or entirely different convective styles is unknown. Theoretical models show that factors such as planetary mass composition, water content, and internal heating can push a planet into different regimes, but the thresholds and combinations that favor plate tectonics remain approximate. This uncertainty raises broader questions about how common planets like Earth might be, and how typical Earth's continental and oceanic evolution is in a cosmic context. Within Earth science itself, several specific questions continue to motivate research into the mechanics and history of plate tectonics. One concerns the exact onset time of fully organized plate tectonics in the early history of the planet. While there is growing evidence for plate-like processes several billions of years ago, the transition from any earlier tectonic regime to the modern style is still poorly constrained. Another concerns the degree to which deep mantle structures such as the large low-velocity provinces have persisted over time and guided the positions of supercontinents and large igneous provinces. A third involves the detailed frictional and mechanical properties of plate boundaries, which control how stress is stored and released, and thus how earthquakes and slow-slip events occur. Each of these lines of investigation feeds back into the broader understanding of how continents and oceans have formed and changed. As data accumulate from improved seismic networks, high-resolution satellite measurements, deeper drilling projects, and refined laboratory experiments at extreme conditions, models of plate tectonics become more detailed, but they also reveal new subtleties and exceptions that must be explained. The emerging picture is one of a planet whose surface rests on a mobile shell, shaped by a complex interplay of internal heat material properties, surface water, and perhaps even biological activity. Continents grow and are modified through collisions, magmatism, and erosion. Oceans are born at ridges deepen as plates cool and subside, and are eventually destroyed at subduction zones. Throughout this cycle, the thin crust records only a fraction of the underlying processes, and that record is continually altered by the very motions it documents. The present distribution of land and sea with familiar coastlines, ocean basins, and mountain chains is therefore a transient arrangement in a much longer narrative. Beneath the apparent stability of everyday geography lies a system in which plates drift, collide, and slide past each other over spans of time far beyond human perception, guided by forces that originate in layers far below the surface. How long this system will continue in its present form, how precisely deep mantle structures and surface configurations are linked, and whether analogous processes operate on other worlds with oceans and rocky shells remain open questions. Plate tectonics explains much about how continents and oceans came to be, but it also points beyond itself toward aspects of the planet's interior and its place among other worlds that are still only partially understood.